G'day mathletes, welcome back to the channel for another extension 2 video. This one is a revision video covering the complex numbers topic, or the initial stages of the complex numbers topic. So if you're a student who has just started extension 2 this term and maybe you have your first assessment task coming up, this could be of good use to you, or maybe you're later on in the course studying for your HSC exam. Either way, hopefully you'll get some value out of this video. We're going to look at 6 different HSC questions. We're going to start with some easier, more straightforward questions and work our way up to a more complicated E3, E4 type questions and see how we can handle them. Okay, as always, the best way to get value out of these videos is to pause the video when the question comes up on the screen, have a go yourself, and then watch as I work through my solution, and hopefully I get the same answer as you and we're both absolute geniuses. Okay, we're going to kick off with a question from the most recent HSC exam at the time of recording, which is 2023. A nice easy band 2 E1 level question. Which of the 4 following is equal to a plus ib to the power of 3? Pause and have a crack if you would like, or just watch along with me if you're feeling like cruising today. Okay, now to expand a plus ib to the power of 3, we can use binomial theorem if you're feeling very brave. Or if you want, you can just go with the lazier option and just go with 3 brackets. If you're really good at binomial theorem, that might be the quicker option, but I know for a lot of people, you might not be quite super comfortable with it yet, and you may prefer just to expand, and so you can just go for that for powers of 3. It's not that hard. All right, expanding out the first 2 brackets, we're going to get a squared, aib, and then aib again, and then I squared, b squared. Simplifying this first bracket, we can combine the 2 iab's together. And don't forget, I squared is minus 1. So we get a squared, 2iab, and then minus b squared. Now we'll multiply everything in this bracket by a, and then multiply everything by ib, and then simplify and see what we're left with. So timesing everything by a, we get a cubed, a squared, and then ab squared here. Timesing everything by ib, we get a squared ib at the front. Then we get 2i squared, ab squared in the middle. And on the end, we get ib cubed. Okay, so simplifying this a little bit more, we can write this I squared in the middle here, the 2i squared we can just write as minus 2. And now we're going to simplify our like terms, and we're going to collect all the real parts together and all the imaginary parts together. So real parts together, we end up with, so simplified, we get a cubed, we get minus 3ab squared by combining these 2 terms here. And then combining these 2 terms here, we get 3i a squared b. And then on the end, we have minus I b cubed. Factoring out the I out of the imaginary parts, and we end up with a cubed minus 3ab squared plus I times 3a squared b minus b cubed, which is option C. So if you opted for option C as well, congratulations, you are off to a cracker of a start. Let's move on to a band 2-3 level question from the 2019 HSC. We've got 2 parts, 4 marks in total. Complex number, -1 plus I root 3. For 2 marks, we want to write that in mod arg form, which is also known as polar form. After we do that, we're going to find the value of z to the power of 3, leaving our answer in Cartesian form. Okay, starting off with part I. You can just chuck this into the calculator if you're feeling really lazy, but if you're not feeling lazy, you're going to draw yourself a little diagram. An eigen diagram to be exact, that looks like this. We've got minus 1 in the real part, and the imaginary part is I root 3, so root 3 up here. Makes us a little triangle. If you are pretty decent with your trigonometry from the advanced course, you'll recognize this as the 1, 2, root 3 triangle. So we have the length of this line here is 2, that's going to be your modulus of the line. And the argument is the angle of rotation around from the positive real axis. So because this is a 1, 2, root 3 triangle, this angle down in this corner here will be 60, which means the angle on the outside must be equal to 120. So we have a modulus of 2, a length of 2, and we have an argument, which is our angle, of 120 degrees, which we'll write as 2 pi on 3. So there is our number in mod arg form. Modulus of 2, argument of 2 pi on 3, and yeah. If any of these questions are unclear to you, I do have full lessons covering all the concepts in this video today. It's just more of a revision, so I'm not going to go super in depth into the explanations. We're just going to go through solutions really today. Okay, part B. Find z to the power of 3, giving your answer in Cartesian form. So anytime you have a complex number in mod arg form or polar form, and you want to apply a power, that is going to be an application of de Moivre's theorem. My class has been telling me I've been saying de Moivre wrong for about 6 years, so apparently it's de Moivre, or something like that. So de Moivre's theorem is that z to the power of 3 is we're applying the power to the modulus and we're multiplying the argument by our power. So 2 at the front is turning into 2 to the power of 3, and the 2 pi on 3 is being multiplied by 3 to make 6 pi on 3. This works out to be 8 at the front. Our angles turn into 2 pi's, and now if we understand what the graphs of cos and sine look like, sine at 2 pi is equal to 0 and cos at 2 pi is equal to 1. So we end up with 1 plus 0i inside the brackets. Expanding it out, we end up with 8 plus 0i. Now I know technically 8 is the answer, but because the question said leave your answer in the form x plus iy, where x and y are real numbers, we have to write 8 plus 0y to be fully satisfying the criteria of the question. So apply de Moivre's theorem, stuff simplifies very nicely and you end up with just 8, which is 8 plus 0i for 2 marks. So not too scary. Let's move on to something more scary. All right, up to a band 3, edging into band 4 question now from the 2021 HSC. Another 2-parter for 4 marks. First part is find the 2 square roots of minus I, giving your answers in the form x plus iy. Once we've done that, we are going to use that to solve this quadratic equation, leaving our solutions in a plus ib form. Okay, starting off with part A. Finding the square root of a complex number is a bit of a process. I do have a video on this, of course, if you need some more practice. It's in the equations with complex numbers video. So to find this, we're trying to figure out some number, x plus iy, so that when we square it, we get an answer of 0 minus I. So this is the complex number with a real part of 0 and an imaginary part of minus 1. If we expand this out, we end up with a couple of equations. We get, so we group the real parts together and we get x squared minus y squared is equal to 0. And we get the 2xy is equal to the minus 1. So expanding left-hand side, comparing the left and right in terms of real versus real and imaginary versus imaginary. We get first equation right there, we get second equation there, okay? Now I explained in the video, but a convenient third equation you can get when you're solving this problem is you can do x squared plus y squared is the modulus of the number that you are trying to find the square root of, okay? Full explanation in the video. That works out to be 1, and so our third equation is x squared plus y squared equals 1. Now the reason we like that one is because equation 1 and equation 3 pair really nice together because we can just add the 2 and the y squareds are going to cancel out. So next step is equation 1 plus equation 3, giving us 2x squared equal to 1. That gets us that x squared is equal to a half, and then x must be equal to plus or minus the square root of a half, which is 1 over square root of 2. Okay, now we have our solutions for x. Let's take the positive one and let's sub it into equation 2 to figure out what the value of y is. Okay, so equation 2 is always the best one to sub into if you don't want to get your positives or negatives mixed up. So into, that should say equation 2. That is a typo, first one already that I'm aware of. Let's see how many more I can smash today. Subbing into equation 2, we have the x becomes a 1 over root 2. So we have 2y over root 2 is equal to minus 1. Okay, so this is equation 2, but I've replaced the x with a 1 over root 2. If we solve this for y, we're going to multiply the root 2 across and then divide the 2 across. So we get y equals minus root 2 over 2. You can simplify this fraction by sort of dividing top and bottom by root 2, and you'll end up with the same thing as x, which is 1 over root 2, but it's negative. All right, so when we subbed in a positive, we got the negative answer. And so then our solutions are 1 over square root of 2 for x, minus 1 over square root of 2 for y, and then because it's a square root, it could be positive or negative, so we have a plus minus, okay? So if you got this statement here in green, that's the correct answer for 2 marks. So yeah, sorry about that. That 3 should be a 2. I should be better than this, but I'm not. And as I always say, you get what you pay for at Mathematics. On to part 2. Using that square root, we are going to solve this quadratic equation. So spicy looking quadratic. Straight away, let's lean right into the quadratic formula, please. This guy right here. Z is equal to negative b, so negative 2, plus or minus the square root of b squared minus 4 times a is 1, and then c is the thing on the end, which is 1 plus I. So that is your c. On the bottom, we have 2 plus a, which is 2 times 1. Simplifying this, we get 4 inside the third, and then we have 4 times 1 plus I with a negative out the front. So we have minus 4 minus 4i. The 4's cancel out, and we end up with the square root of minus 4i inside our square root, inside our radical term. We can simplify that a bit by writing that as the square root of negative I multiplied by the square root of 4. So just splitting apart this third. Now this is good news because that turns into a 2, and then there's a 2 here, a 2 here, and a 2 here. So we can divide everything by 2, and it turns it into negative 1 plus or minus the square root of, that should say minus I. That's mistake number 2. Going so well. And on the bottom we've got 1. So the fraction vanishes away and life gets a bit easier. Now pretending that I actually wrote that as the square root of minus I as it should be, we know what the square root of minus I is. It's up here from part I. We can sub this into our solution. So we have minus 1 plus or minus our square root from part I, which is right here. Now we're more or less done, but the hard part is we've got to write our two answers, one with the plus, one with the minus. And we've got to write them in A plus IB form. So we've got to simplify our answer quite a lot, which is pretty challenging. A lot of surds, a lot of fractions, all the good stuff that we're used to in Extension 2 maths. So first case, we're going to do the plus. Now a clever way of writing negative 1 is to write this as root 2 over root 2. This is so it has the same base as our real part, and we can combine these together. So combining these together, we're going to have 1 minus root 2 all over a common base of root 2, and the imaginary part is 1 over root 2. So there's our first solution using the plus. The second one using the minus, and once again writing minus 1 as minus root 2 over 2. Combining these two terms together, we'll get a negative out the front of 1 plus root 2 on the top, root 2 on the bottom, and the imaginary part is now positive. Okay, so that line there in red and that line there in green are our two final answers to get us 2 out of 2 marks from this 2021 HSC question. So a little bit of a spin on the regular square roots questions, but as long as you understand the process of finding square roots, these are usually fairly straightforward marks as long as you can remember the steps, do them in the right order, and just be confident with your algebra, really, which is good life advice, I suppose. All right, 2 mistakes down, probably 4 more to come. Let's move on to a band 4 question from the 2020 HSC. Okay, another multiple choice question. We've got, what is the maximum value of modulus of a number minus 2 plus modulus of a number plus 2 for theta between 0 and 2 pi? Okay, this is a question where online the solution that I looked at to check mine was very algebraic and looked very confusing. I actually found this question much simpler to approach from a geometric standpoint, okay? The way we're meant to look at this is we're meant to say that e to the I theta is a complex number. It's in exponential form, so the thing out the front is your modulus, and because there's nothing out the front, there's an invisible 1. So e to the I theta has a modulus of 1 and has an argument of theta. Now, the way we're meant to interpret the absolute value of e to the I theta minus 2 is we're meant to say that this is the distance between this number and the number 2. And this one right here is the distance from this complex number to the number minus 2. Okay? You may not have encountered this in your first topic of complex numbers, but most people do this later in the year. So if this is making no sense right now, you can skip to the next one because this is more of a geometric application rather than an algebraic one. Okay, but here's the basic info we need for this question. This is a complex number with argument theta, modulus 1. This means distance from 2, and this means distance from minus 2. Now, if we convert this into what I like to call proof by diagram, we have an argand diagram, and here is a circle representing all the numbers that have a modulus of 1 and an angle of theta, basically. Okay? Now, here is 2, and here is minus 2. Now, we're trying to find a point on this circle that has the maximum distance from these two red dots when we add them together. So if you think about it, when you do a bit of sneaky little mental trial and error, this number up here is going to be the go because it is the maximized distance from the red dot on the left and the maximized distance from the red dot on the right. If we had one in the middle here, we would have, it'd be like 3 away from here and it would be 1 away from here. So it would be 4, which is B. But B is not the biggest possibility, okay? These two red lines added together will be bigger than 4. The way we're going to figure out their length is we are going to do some Pythagoras and say, well, this red line, this dotted red line, is the square root of 2 squared plus 1 squared in this right angle triangle. That works out to be the square root of 5, okay? So this red line here has a distance of root 5. Because we're adding this red line and this red line together to get the sum in the question, you know, this distance plus this distance, Root 5 plus root 5 works out to be 2 root 5, and that's why C is the correct answer. Okay? So the reason I wanted to show this question is because if you approach this algebraically, it is quite complicated and quite challenging. If you just understand the geometry of the question and just draw a quick little diagram, you can get your answer relatively quickly, which is why I think it makes a good multiple choice question, because it has a shortcut. I like that. A shortcut to a 1 mark is a huge win.
Okay, let's continue our suffering by moving on to the E4 level question, starting off with a band 5 from the 2016 HSC multiple choice. Okay, this question is an absolute stitch up of value because we're about to put in about 3 or 4 marks worth of effort to get a 1 mark multiple choice question, so we may as well have just guessed. So fun, just guess now and see if you get it right, and then you might have saved 10 minutes of your life. Okay, we have an equation, x plus 1 over x is equal to minus 1. We're asked to find the value of x to the 2016 plus 1 over x to the power of 2016. Okay, so the way we're going to tackle this behemoth of a multiple choice is we are going to use the equation given in the question to solve for x and figure out what the value or values of x are, that we can apply these to a power of 2016 using de Moivre's theorem, as we say in Francais. So starting off with our equation, we are going to multiply everything on the left and right hand side by x to make it look like this. X squared plus 1 equals minus x. Because we have a quadratic, as is good manners, we should chuck everything over on the left hand side. Now we have a quadratic that is non-factorizable, and completing the square makes me cry, so I'm going to use the quadratic formula instead. In this case, a, b, and c are all equal to positive 1. So here's our quadratic formula, minus b squared 4ac all over 2a. When we simplify this, we get minus 1 plus or minus the square root of minus 3 over 2. Now, square root of minus 3 used to frighten us, but now we are mighty extension 2 students, and we know that the square root of minus 3 is equal to root 3i. So we write our answers as minus 1 over 2 plus or minus root 3i over 2. So there are our two values for x. Now we want to figure out, if you remember the question, we're trying to apply a power of 2016 to this, which means we're going to be using de Moivre's theorem, which means we need to be putting our number into polar form or modarg form. So first thing we'll do is we'll calculate the argument by squaring these two components. Squaring this turns into a quarter. Squaring this turns into 3 over 4. If we add those together, we conveniently get 1, and the square root of 1 is indeed equal to 1. So both of these complex numbers, plus or minus, will have a length of 1 from 0. Now I'm too lazy to do a diagram in the video, but if you do a little diagram of this triangle in the second quadrant, you'll get the 1 root 3 2 triangle shape with the 60 degrees that we saw similar to the earlier example I did about 15 years ago. Okay, so if you compute that, the angle inside the triangle is 60, the angle outside the triangle, is 120. So one of our arguments is 2 pi on 3, and because we have a plus or a minus, we have a plus here and we have a minus here. Now this one is in polar form, it's good to go. This one is not in polar form because there's a minus in the middle there. So we'll just put minuses inside the angles like this. Remember, cos of a positive angle and negative angle is the same thing. And with sine, because it's an odd function, you can put the negative inside the angle like this. So going from this line to the line above is just applying even function properties and odd function properties. Okay, now they're in polar form. Now we can simplify them a bit and just say our modulus is 1, our argument is 2 pi on 3, either positive or negative. So our two numbers are cos I sine plus or minus 2 pi on 3. Now we're going to give this a big dirty power of 2016. So let's make some space. Okay, applying a power here, we know we're going to do the modulus to the power of 2016, which will still be 1. And we're going to multiply the argument by 2016, which looks like this. Would you believe that 2/3 of 2016 is indeed 1,344? And would you believe that 1,344 is actually 672 lots of 2 pi? The reason this is important is because this number is essentially equivalent to cos I sine of 2 pi, and cos I sine of 2 pi is equal to 1, because cos of 2 pi is 1 and sine of 2 pi is 0. So this whole thing really just turns into 1. So now we can actually answer the question and say x to the 2016 is 1 plus 1 over 1. So we get 1 plus 1. So we get 2. And if that's what you guessed 5 minutes ago, congratulations on the pain and suffering and time you just saved in your life, and you are born lucky. Okay, finishing off, trying to land this plane with a band 6 question from 2022. This is a full-blown E4. I'm pretty sure this was the last question in the 2022 exam. We're trying to find three numbers, Z1, Z2, Z3, that satisfy, they all have the same argument, they add to give 1, and they multiply to give 1. Now, as is always the tradition with the last question in the HSC, the first thing you ask yourself is, where do I even begin? How do I even start to tackle this thing? And the trick to this question is to recognize that here you're adding three numbers and here you're multiplying three numbers. And hopefully, maybe, if you're lucky, this gives you some Vietnam style flashbacks of the sum and product of roots. This is the sum of three numbers and this is the product of three numbers. So we're essentially going to try and find a polynomial that has these three numbers as roots so that we can figure out what they are. Okay, we have the sum individually, we have the product. The goal of this question is to figure out what the product in pairs is. Z1 times Z2 plus etc. Okay, so we have the singles, we have the triples, we're trying to find the doubles. Here's how we do it. It's an absolute experience. Let's dive right in. First thing we're going to say is that because the question told us the product is equal to 1, we can take the modulus of this equation and say the modulus of both sides. Modulus of 1 is equal to 1, and we can split apart the modulus on the left-hand side into this. Okay? Now, because the question said the moduli are all equal, we can actually just write the left-hand side as the modulus of either one of these. I'm going to go with Z1. We can just call this Z1 cubed. This allows us to solve and do the cube root of both sides and say that the modulus of Z1 is equal to 1, which means so is Z2 and Z3. So straight away we have some information and we've got one of the 3 marks. I forgot to say here this is a 3-mark question, sorry. Similar results for 2 and 3. Okay, now we're going to say that because these complex numbers have a modulus of 1, if we wrote them in exponential form, they would look like this. Modulus of 1, argument of theta. Now we can take the reciprocal of both sides and say 1 over Z1 is 1 over e to the I theta, which is e to the minus I theta. Okay, this is changing the argument from positive to negative, which is telling us that this is the conjugate. Okay, changing the argument from positive to negative is flipping across the real axis, so you're doing the conjugate. So this proves that if we take the reciprocal of Z1, we get the the conjugate of Z1, and we get similar results for 2 and 3. So taking the reciprocal of any of our 3 numbers gets us our modulus. Our conjugate. I'm getting lost in my lingo here. Okay, this is useful because now we can go back to the product equal to 1, and we can divide both sides by Z3. Okay, so we get Z1, Z2 equal to 1 over Z3. And 1 over Z3, as we established in the green section here, is equivalent to the conjugate of Z. Have I lost you yet? I hope not. I've kind of lost myself. All right, using this equivalence here, we get similar relationships for Z2, Z3 and Z1, Z3. Okay, this is cool because now we have 3 expressions that we can add together, and now we'll have an expression for the product of Z1, Z2, Z3 in pairs, which, if you recall, was kind of the goal of this whole question, to form this into a polynomial of sorts. Oh my god, I'm starting to have night terrors. Okay, so adding these together is the same thing as doing the 3 conjugates plus together. And a cool little property here is when you take the conjugate of 3 numbers and you plus them together, it's the same thing as doing the conjugate of all 3. Okay, so this is a property of complex numbers. It's a bit niche, but it is very useful here. This is good because we know that the sum of these 3 is equal to 1, and we know the conjugate of 1 is equal to 1. And so there you go. We've successfully ascertained that the sum of the product in pairs of these 3 numbers is equal to 1. Now we really have all we need. We have that the sum of the individual numbers is 1, and in terms of a polynomial, this is always equal to minus b over a, okay, the sum individually. The sum in pairs we've established in red is also equal to 1, so that means c over a is equal to 1. And the product is equal to 1, and that's going to be negative d over a in terms of a cubic polynomial with 3 roots, z1, z2, z3. So now, if, that was weird. Now, if we have these 3 established, if we say that a is equal to 1, just to make it convenient, that gives us that negative b is 1, c is 1, and negative d is 1, which gets us b equals minus 1, c equals 1, and d equals minus 1. Now we have the 4 coefficients of our cubic polynomial, which means it looks like this. A is 1, b is minus 1, c is 1, and d is minus 1. Now we just need to solve this polynomial, which is actually pretty easy because this is actually kind of convenient to factorize. We can take z squared out of the front pair, And then if you put brackets around this, you can see we have a common factor of z minus 1. We can factor that out the front, giving us z squared plus 1. Now we're going to write z squared plus 1 as z squared minus I squared, so we can use the difference of squares here to factorize this thing completely. Factorizing this, we get z plus 1, z minus I, z plus I. And now if this expression is equal to 0, it means that z must be equal to 1, I, and minus I. And those are our three solutions, which actually maybe you could have guessed. I doubt that would give you 3 marks for guessing that, but it is a valid way of getting a solution if you can just see it, if you're just gifted. But yeah, that's how we get a Band 6 question done in 2022, just recognizing that this is sort of guiding you towards making and solving a polynomial to figure out what Z1, Z2, and Z3 are. Well done if you got that. I know I certainly wouldn't have, but I'm not a Band 6 student. That's why I'm a maths teacher. Haha, comedy. All right, thank you for watching. I hope that enhanced your understanding of complex numbers. Hope you got some value out of that, and I look forward to seeing you in some further revision videos for the extension courses. Bye for now, and not forever.